Welcome everyone. So in the last lecture of Agniva, so today we'll talk about Hartog extension theorem in SCV. Over to you, Agniva.
Yes, thank you very much. Okay, let me just join it from my tab. Yes. The screen. Is it visible?
Yes.
Okay, good. So, all right. So, let's start where we actually left off last time. So, last time we saw that we end our discussion on the domain of convergence of the power series. And we saw that a domain of convergence of a power series has to be a complete Reinhardt domain. And in particular, it has to be a log convex domain or a logarithmically convex domain. And that actually gives us another thing is that that not for all domains, we should not expect that if I take a holomorphic function, that holomorphic function won't extend beyond that domain. So there are domains where every holomorphic function sort of extend to larger domains. And that raises the question of weak, or rather definition of weak domain of holomorphy and domain of holomorphy. And we last time discussed that every domain in complex plane is actually a domain of holomorphy and weak domain of holomorphy. And last time I actually finished my talk at the end with the Hartogs extension theorem, which is the main topic, central topic of today's talk. And what is the Hartogs extension theorem saying is that you cannot have a compact singularity of a holomorphic function. So if you have a like in complex analysis, if you have a function which is bounded and it has a removable singularity, you basically extend it to on the domain, right? The whole domain. I mean, there is no bounded removable singularity, but it's saying in Hartog extension theorem is saying that there are no compact. I mean, this is in higher dimension. There are no compact singularity of a holomorphic function. Which what does that mean? So formally, this is also last time I also stated. So suppose you have a domain in Cn, and most important thing is that n is greater than or equal to 2, because in one dimension you won't have that. Every domain is a domain of holomorphy. And if n is greater than or equal to 2 and omega is a domain and k is a compact subset of omega, such that omega minus k is, just change the orientation, and omega minus k is connected. And suppose you have a holomorphic function on this annular region, that is omega minus k, a holomorphic function, then there exists a holomorphic function on the full domain, which coincides with small f on the annular region. So if k is this green compact domain and omega is this orange, the region inside this orange part, then if you take a holomorphic function on this white region, then any holomorphic function extends to all omega. So basically, every holomorphic function which is holomorphic in omega minus k, and omega minus k is connected. That is very important. You can immediately construct a holomorphic function if omega minus k is not connected. So basically, take the sphere and take the unit, say a larger ball or something like that, and just remove the sphere from it. That is not omega minus k is not connected, and on the two disconnected component, you define two different holomorphic functions such that it does not extend. So you can always have a counter example when omega minus k is not connected, but when omega minus k is connected, if you have a holomorphic function, that holomorphic function always extend to the larger domain. So basically this says that omega minus k, this is basically saying that omega minus k is not a this is not a domain of holomorphic. So this is never a domain of holomorphic. So sort of annular regions are never a domain of holomorphic. The important point over here is that how the proof goes. So the proof is actually allow me to define or rather introduce you multiple things. So the first thing is what I am to talk about is what known as the D-bar problem. So this is about the D-bar problem. So what is Del-bar problem? Now what I am going to talk about is a very baby version of the original or the full general Del-bar problem. But what does this mean? This is sort of a Dirichlet problem. I think everybody has seen a Dirichlet problem. Right? What is a Dirichlet problem? It basically asks for uh, solving something on the Laplacian of u equal to f, right? I mean, this is what the Dirichlet problem is on some domain omega. Now here you replace this by a sort of a complex or rather a the Dirichlet problem is a two. I mean it's a second order differential equation. But here you are actually allowing a one single order differential equation. But this is called the D-bar problem. So how the del bar is defined? Now those of you who have seen the operator del bar as a uh, what known as the differential forms or something like that, or in terms of tangent spaces or sections of tangent spaces, this can be defined in that fashion also. But if you haven't, those of you are not familiar with those language of manifolds or tangent spaces or tangent bundles, then this del z bar is basically defined as del x plus I times del y. That's the operator. And you can see that if you have a function, so this is in complex plane in C. So if the function is zero, this is basically means that f satisfies the Cauchy-Riemann equation. Satisfies the Cauchy-Riemann equation. So if you can write f equal to u plus iv, and if del f del z bar equal to zero, then you can see that that basically same as saying it's the Cauchy-Riemann equation. So that basically means that f is holomorphic. So sometimes you will see that it enough when you say something is holomorphic, you can basically say that a function which is killed by the del z operator is called a holomorphic function. Now in higher dimension, basically we know, right, that in the first talk we discussed that what is the definition of holomorphic function in higher dimension is it's separately analytic, right? So if I just defined, so it basically means that if I simply defined this, that at each variable, if I define this, then a holomorphic function, so j is running from 1 to n. A holomorphic function f basically means, so if f is say from omega to c, and here your omega is sitting inside cn, then a holomorphic function basically means that it's killed by all of this operator for all j running from 1 to n. It's like at each variable, it is separately analytic or separately holomorphic. That's what holomorphicity is, right? So what is D-bar problem? So D-bar problem means, so this is just a very heuristic, what I'm saying it's not at all precise, but what D-bar problem basically means that you suppose you have a G is a data on omega. So basically I am asking find an F such that this happens. So it's exactly like the Dirichlet problem, but for a different operator. So that's sort of the sorry, my bad. This is in one complex variable. So this is omega in n equal to 1. In n greater than 1, this is what I'm asking. This is what D-bar problem basically means. In n greater than 1, so
Sorry, what
when
is
n
G?
is
G is in L2 or is smooth?
no, nothing is in L2. I just said some data. I haven't precised it at all. I just said that
Okay.
it's some data, and this is what basically a D-bar problem means. Now we'll talk about the smoothness and all those things later on.
Okay. Mhm.
And when n is greater than 1, you basically have now, because there are like n many, so there are n many operators, right? Del z1 bar up to del zn bar. So there are n many operators. Now, basically, what you ask is that suppose you have n many data, gn data on omega, then basically ask for a function f. So find f find f on omega such that this happens. Equal to for all j running from 1 to n. So I hope this is clear. Now, in higher dimension, there is something more going to happen. So there is from this only from this information you can deduce something more. So suppose now I come to Ravi's point. So suppose GJs are, for the time being, if I assume that GJs are say smooth. So GJs are a smooth function on omega. And suppose I found a f. So suppose you basically don't need smooth. I think C1 is enough or continuous is enough. Suppose you find a, so just take continuous for the time being. Or maybe, okay, no, take smooth for the time being. Or suppose you get a function f, which is also smooth in omega and satisfies this equation. I think you can basically take Gj to be C1 and F to be C2 for the time. And this satisfies this. I'm just going backwards. Okay. So suppose your Gjs are in C infinity smooth functions, and you fortunately you get a function f which is C infinity smooth. Then if I apply the double derivative, that if I apply the kth derivative now, this should satisfy. But because f is a smooth function, this is same as I can reverse the order, right? If I have a smooth function or a C2 smooth function, I can actually reverse the order of the differentiation of the when I do partial differentiation. I can change, I can reverse the order, but this is same as del j gk del zj bar. So that basically means that these two has to be equal for all j not equal to k. This is called the compatibility condition. So to expect if you expect that such a f exists, you need to put an extra condition on Gj. What is the condition? This condition is this compatibility condition. Because there are only one variable in one variable, you don't need this compatibility condition in one variable. But here you need, because you have more variables, you need this compatibility condition for higher variables. So this is called the compatibility condition. Compatibility condition. Okay. So now let's digress a little bit. So we'll talk about this D-bar problem with a little bit more generality. But let's digress a little bit and let's go to one of the key tool of complex analysis. So again, n equal to 1. And this is a way to solve D-bar problem in n equal to 1. This is called the generalized Cauchy integral formula. Now I'm not going to give a proof of this, but I mean you can find the proof in. I'll refer some books. So what is this? So when I was doing complex analysis for the first time, I used to make a mistake a lot of time. What is that? So suppose you have given a holomorphic function, and by chance you are given that the function is continuous up to the boundary. I mean, there are multiple times you will see this. So omega is a subset of C. It's a domain in C. I mean, you will see this setup in multiple times. That's the holomorphic function continuous up to the boundary. What I used to do all the time, I try to write fz like this. I always used to write this, but this is not essentially correct. If you just do a complex analysis course, you probably haven't, you should not write this. What is the difference? So when I talk about Cauchy integral formula, this is not the Cauchy integral formula, by the way. The big difference over here is that I have writing the integral on the boundary of omega. The Cauchy integral formula basically says that you go to a smaller domain, or you go to a smaller ball or a disk, and then on the boundary of the disk, you apply the Cauchy integral formula. You cannot just replace the Cauchy integral formula to boundary of omega. But if you do this change, boundary of omega, you will see that many and many problems are very easily solvable. For example, the function is say 0 on the boundary. You can immediately say that, okay, the function is 0 everywhere. So here z is in omega, by the way, because f is 0 on the boundary. So, so can I justify this somehow? The answer is yes, you can. And that's what a generalized Cauchy integral formula means. The only thing is you need a boundary regularity of the domain. So what is that? So suppose, so it's theorem. So suppose omega is a bounded domain in C, which is C1 smooth. So what does this C1 smooth means? It means that boundary of omega is a C1 smooth manifold. So if you really locally look the graph of the boundary, it's a graph over a C1 smooth function, which is C1 smooth. Then and f is a C1 function in omega closure, then fz can be written as 1 by 2 pi I boundary omega f zeta by zeta minus z d zeta minus 1 by pi. So one integral is on the boundary, the next integral is a volume integral. So it's on the omega, domain omega. So it's del f del zeta bar of zeta divided by zeta minus z dv zeta for all z in omega. So this is those of you who have done a basic PDE course, you probably have seen this in the setting of Dirichlet problem or the Laplacian, which is known as the Cauchy-Green formula. There are some probably Green's, there are some Green's formula, right? So this is one of the version of Green's formula, but the only difference there is that this del f del zeta bar is replaced by the Laplacian. So this formula, if you have this formula, that's the theorem that if you have a function which is C1 on the omega closure, then you can write down f like this. You can represent f like this. This is one way of integral representation. You can see that remark, if f is holomorphic, if f is holomorphic in omega, which is same as saying that del f del zeta bar is equal to 0. So the second term is actually gone. So that basically means that fz can be written as 1 by 2 pi I boundary of omega f zeta by zeta minus z d zeta. Now what I have done over here is that f is holomorphic omega and continue C1 up to the omega closure, then you can do this. Now you can do an approximation of a continuous function up to the boundary with a C1 function. And then you can actually write down this for any holomorphic function that are continuous up to the boundary. You don't need this C1 condition. So I hope this is clear. This is called a generalized Cauchy integral formula. Why is a generalized Cauchy integral formula? Because you can actually writing down a Cauchy integral type formula for any C1 function up to the up in the omega closure. That's it. This formula will actually give me the solution of the del bar problem for a very specific, which is known as the compactly supported setting. So if my data is a compactly supported data, then I can actually get a solution of the del bar problem that I just stated. Now,
Sorry,
a bit of
could you
heuristic.
explain how do you approach if we have a continuous function just to omega
So
closure?
what you do, you basically shrink the domain. You don't approx
Mhm.
f, but rather you sort of shrink the domain. And
Okay.
once you shrink the domain, there the function will be holomorphic up to the omega closure. So in the shrink domain.
I see. Okay.
So then you apply a sort of a DCT to get the result.
Okay.
So basically, you sort of cover the omega or sort of an exhaust omega with a C1 smooth
Yeah,
domain.
then you have to take some
And
scaling, means you have to define Fn with respect to some scaling, right?
yeah, some
Means you
scaling.
have to
Yes.
find some Fn, but
Yes,
that
exactly.
scaling, we also need that scaling should be holomorphic, is it?
We need that scaling should be, no, we don't need that scaling should be holomorphic. Uh,
We need, okay,
Isn't
right, but I think you can do that if I correctly recall.
I see.
I am
Because
pretty
we
sure
need
that
Fn
it's
is holomorphic on omega.
correct. But I am pretty sure that that's how it goes. If I correctly recall,
Uh,
it's not very difficult.
I see.
I can show that.
Okay.
It's not very difficult. I need to think a little bit, but
Yeah,
the
sure,
scaling is
sure.
the correct way, I guess. I mean, shrinking the domain and then do it.
Yeah, I'm just little bit worried about this holomorphic scaling here.
I
Ravi?
understand, but I am pretty sure that holomorphic scaling may not be the correct way to do it, but this
Uh,
sort of shrinking is the correct way. I correctly recall.
Basically. Yes, shrinking means this thing, like distance of x to the boundary omega is say less than epsilon or greater than epsilon. This type
Yes.
of shrinking. Yeah,
Yeah, I think so. I need to think a little bit more.
yeah, sure.
Yeah.
Agniva and Ravi,
Yeah.
I'm just doubtful what Ravi asked. So is it like kind of asking these C2 smooth function with compact supports are dense in L2?
C2 smooth functions are
With,
compact support.
with compact support is dense in L2. I mean, that's what is going on,
No,
no?
no, no, no.
No,
No,
that
we
is
need
not.
holomorphic function also.
Uh, yeah, I need the holomorphicity over here because I need to kill this del f del zeta bar.
Yeah, otherwise you can use this convolution to get
Yeah,
just a
you
smooth
can
thing.
always do that by taking the convolution of the
Okay,
cutoff
okay.
functions.
Okay.
Yeah.
Okay, thank you.
So, okay. So, let's let's do this. What I was talking about? Ravi, I need to. I have one comment. So basically, what you
Yeah.
do, you take omega and you take omega and take the exhaustion of with some smooth domain and restrict. So you basically Fn of z
Mhm.
should be f restricted on omega n. This function is
Okay.
holomorphic in omega n closure because it's already holomorphic in omega.
Yes, it is holomorphic in omega n. Yeah.
It will be holomorphic in omega n. Apply the generalized Cauchy integral formula on the omega n, boundary of omega n. So you will get fn z will be 1 by 2 pi I integral boundary of omega n fn is basically f, right? So f zeta minus z d zeta. Now push n towards infinity and get boundary of omega.
Okay. So you are okay. You are
I'm not
approximating
using
the
a
domain,
scaling
not
to bring it
function.
down.
Okay.
I'm just
Yes.
restricting the function on the smaller domain.
Got it. Nice.
Yeah. So, all right. So let's talk about a heuristic that how this actually solves. So this is absolutely again a heuristic. This is again not something formal. So what I want to solve. So I want to solve this problem. Where did I write this problem? Right. I want to solve this problem. So suppose I I want to solve this for this kind of function. They are compactly supported smooth functions. What I ask that find an f such that del f del zeta bar equal to g on say C, on full C, right? Now, what happens over here? Suppose I want F to be also compactly supported. This is not a very good ask actually. We should not demand this. We'll see that, but we should not demand this. But suppose I want that for a compactly supported data, the solution should be compactly supported. Then what happens? So this F will be compactly supported. So the support of F will be sitting inside a large ball, some large R. I apply the generalized Cauchy integral formula on this. So if I do that, what happens? That Fz, so by GCIF, Fz can be written as boundary of B0R, F zeta divided by zeta minus Z, d zeta, plus or minus, whatever the way I have written, minus 1 by pi, 1 by 2 pi I. This is B0R del F del zeta bar divided by zeta minus Z. Zeta, this is dv zeta. Now, because the support of F is actually contained in the boundary in the B0R, F is basically 0 on the boundary. So F is 0 on the boundary of this ball or the disk. I'm in complex plane. Okay. So this is 0. What I am asking, I was asking del F del Z bar equal to G. So this guy here, this should be G. So this is G zeta. That basically what happens over here. So Fz, if that thing happens, Fz will be minus 1 by pi B0R. And the point is you don't have to write B0R, you can actually write C, but anyway, write B0R for the time being. This. That means what does basically this say? That it basically says that this has to be the solution. This thing has to be the solution. So that means, but I can always write B0R to be C because I mean, G is compactly supported, right? I can just write the as a C, I mean, as a whole integral, doesn't matter. So that basically means that this thing, this operator, this integral operator is going to be a candidate for your solution of the D-bar problem in a compactly supported setting. So here is the theorem. So this is a very common technique in PD that you basically put, suppose this is a solution, and then you can get a form of that solution. I mean, this happens a lot of time in PD. That to solve a PD, you basically assume that okay, if this is the solution, what does it looks like? So this is how it looks like. So this is going to be the solution. So theorem. So suppose omega is a, oh, there is no omega, I don't have to. So G is a CC infinity function in C. Then there exists a U such that this is in fact going to be C infinity in C such that Fz, del U del Z bar is equal to G on C. Important point is that outside the support of G, U is going to be holomorphic because del U del Z bar is going to be 0. So U is holomorphic outside. There is a remark actually. Outside the support of G. How am I getting this C infinity smoothness? Is that because this is an integral, somehow or some way or another, I'm not going to explain that, you can take a look, but somewhere or another, I have to push the derivative inside. I need to push the derivative inside, which is known as a Lipnitz law that how do you actually push a derivative inside the integral? A priori, it won't work, the Leibniz law, but after a change of variable, you can actually minimize this singularity of the integral. Currently, the singularity is very large. It's actually for all zeta equal to z, the singularity persists. But if you change a variable, just zeta goes to z, zeta plus z, then the singularity become at a single point. So that is why what you can apply the Leibniz law or sort of a generalized version of Leibniz law to prove this theorem. Number two, you may not be compactly supported. So now if this is the solution, you can actually see that for any compactly supported data, this integral may not be, or this function may not be a compactly supported function. It will be always a smooth function, but may not be a compactly supported function. So that's what happens in one variable. Now I go to the higher variable. So if I go to the higher variable, the number of equations will increase and I have the compatibility condition. So theorem. So suppose this is n is, yeah, your question?
Here G is smooth can be with the smoothness. Maybe if it is C1, C2, will it hold?
It will hold. So for example, if you take, the smoothness will go down to even L2, what is known as in the sense of distribution, but it will hold. If you just, for the time being, if you just take G to be, say, C1, then C1 compactly supported, then you will be a continuous, sorry, my bad. If you take G to be just a CC infinity function, if you just take G to be CC infinity, CC
C1.
function in C, then you will be a C1 function in C. Yes, this will hold.
Oh, okay.
Yeah, but it will go down much below than continuity. It will go down to what known as the L2 sense.
Okay.
Anyway, yeah. So theorem. So this is in higher dimension. So n is greater than equal to 2. It doesn't matter. I mean, n is equal to 1 is also works. So suppose so you have n many data. G1 to Gn is CC infinity in Cn. CC infinity in Cn. Then there exists a U C infinity in Cn such that, my bad. Sorry. Such that it satisfies the compatibility condition that Zk bar equal to Zj, Zk, Zj bar for all j not equal to k. Then there exists a U C infinity in Cn such that du del Zj bar equal to G on Cn. The striking difference over here is this. I can make it compactly supported. So in higher variable, you can make it compact. The solution is going to be a compactly supported solution. You'll get a compactly supported solution. So how does the proof goes? Proof goes via the one variable one. I mean, it uses the one variable result. So how does the proof goes? The proof is very interesting. Proof is, just cook up the exact solution. It's just C G1 and divided by dV of W. Now you will say, if you look at this, you will say that, okay, if this is the solution, how can this be the solution? Because it contains only G1. I mean, it solves for all J, right? It solves for all J, it solves for all Gj, but your solution only contains G1. And this is striking. And that's where this compatibility condition comes to the picture. So what happens over here? So by the previous result, or the one variable result, you can immediately conclude that this thing is going to be G1 and U is going to be C infinity. That you can conclude that if I take the derivative with respect to Z1 bar, that's going to be G1. Because the Z2 and up to Zn are actually fixed, by the way. I mean, fixed means it's basically, so Z is equal to Z1 up to Zn. Now, if you take the double derivative, if you take the derivative with respect to any other variable, say J bar, I'm writing something, I'm not justifying it fully, but if you just believe me for the time being, if I take its derivative with respect to the next, I mean, some other variable, so J is not equal to 1, then it will hit it over here. So the other variables are, I mean, the integration is not happening on the other variable. So I can actually take the derivative inside. If I take the derivative inside, now what I can do, I have the compatibility condition, and that's why the compatibility condition come into the picture. I can replace this by this, that I can actually replace G1 with respect to the jth variable. I can replace it the jth one with respect to the first variable. So now you apply the GCIF. So this is GCIF, and you will basically get Gj. So it's a very beautiful proof. Now the point is, why CC infinity? Why compactly supported? The reason is that if you really look at this thing, this Z2 to Zn are basically fixed, right? So if I take, so the point over here, so I just write down in terms of the remark. So remark that U is compactly supported on compactly supported, okay? And the support of U is contained in union of support of GJs. What I'm saying over here is that U is basically the support of U basically contains in the union of support of G's. Why? Because if I really look at the other variable, the other variables are fixed. They are just Z2 to Zn. So if I take a very large Z2, for example, if I take a very large Z2, which is outside the G1, which is outside the support of G1, then and outside the support of outside the support of G1, then this is going to be 0. This whole function going to be 0. So U is going to be 0 outside a very large ball. Is it clear what's happening? Because of these fixed variables, Z2 to Zn, it's actually becoming compactly supported. Number 2, is it clear? I pause for a few seconds because it's if you're looking this for the so what is happening over here? So see that all the GJs are compactly supported, right? All the GJs. So let's go to two variables. Suppose you have G1 and G2. So both of them are compactly supported. Now you consider this function G1, say W Z2 divided by W minus Z1. And I'm integrating it over, say, C. Oh, yeah. Now you see that it's W1, W1. If I take a very large Z2, then what will happen? And very large W1 also. So the point is, if I take a very, very large Z2, say somewhere over here, and the support of G1 is say somewhere over here, right? Support of G1 is a compactly supported, right? So G1 is something like this. If I take a very large Z2, it will once cross this square. It will always go outside the square. Now you take any W1, it doesn't matter because once this Z2 is very large, you take any W1, this is completely zero. This thing is completely zero. So if this function is completely zero, that basically means what? That basically means that this u is completely zero outside a very large square. That's what happening for all the variables. Is it clear now?
Yeah.
Yeah. So that's what happened. So now you can actually say that this is a compactly supported function in higher dimension. And that's the key change why Hartogs extension theorem does not hold in one variable and holds in higher dimension. So this is a very nice exercise. If I will write down the steps of the Hartogs extension theorem, and it's a very nice exercise, and probably all the books actually ask this. That's where the proof actually fails for one dimension, and this is where it actually fails. So proof of Hartogs extension theorem. So proof of Hartogs extension theorem. So what you're going to do? So what is the Hartogs extension theorem again? So you have a K compact set. K is compact. Omega minus K is connected. So let's draw a picture. Suppose this is your omega. This box is say K. This is omega. What I'm saying, if a function is holomorphic in this region, it has to be holomorphic in the whole region. How do you do it? So suppose f is a holomorphic function in omega minus K. I need to find an extension. What I'm going to do first, I'm looking for a holomorphic extension, right? What I'm going to do, I'm going to take an smooth extension first. I'm going to take a smooth extension first and then somehow cook up an holomorphic function. And this idea of first taking a smooth function and then go to holomorphic function is what makes this proof very, very important, because this is why D-bar problem is so important, because D-bar problem is actually allows you to create holomorphic functions from some smooth data. Now what happens over here, you need to, so how do you extend something? How do you extend a continuous function to smoothly, not holomorphically, smoothly to a larger domain? Basically take a product with the cutoff function, right? Or the modifiers, what PDE people says. So what you do? So you take a cutoff function x, which is CC infinity in Cn, such that number one, the properties are it has to be 1 on U. So what is U? Let's draw U. So U is a neighborhood around K. This is U. And V is a larger neighborhood which is containing K. Which color? Maybe this. So this is V. So what is this? So K is sitting inside U, U is sitting inside V, V is sitting inside omega. This double subset basically means that the closure is actually in the V. Okay, so X is 1 on U. Number 2, X is 0 on omega minus v closure. You can always construct a cutoff function like this. In fact, cutoff function, or maybe I can do better. I can take Cn minus v closure. Cutoff functions are basically like this. So cutoff functions are basically like this, that cutoff function basically says that you can construct a function which is around a compact set, it is 1. After that, you don't know. In this part, the value is you don't know what happens in this region. But outside of that, it's completely 0. Step 1. This is smooth extension of small f. So what you do, you basically multiply it with the function small f. So how do you multiply? It's like f set, you just define this function, 1 minus the cutoff function. Cutoff functions are always between 0 and 1. So cutoff functions are always between 0 and 1. Times f set when z is in omega minus u, and it's 0 when z is in u. So I just extended this function, making sure that near the boundary of omega, it is just the function small f. Okay. Then capital F is a C infinity function in omega, because I just multiplied it with a cutoff function, so it's a C infinity. Now I need to come up with a data to solve the Debye problem. Okay. The point is, this is not going to solve the problem. So what I'm going to do, so this is an extension, by the way. This is a smooth extension, but I want a holomorphic extension, right? I want a holomorphic function, which is, so we want ff, which is holomorphic in omega, such that ff is small f on omega minus k. So, so how do you do that? So you construct this datas. This is simply del f del zj bar. This is on omega, and 0 on Cn minus omega. So GJs become compactly supported and smooth. Now this, why GJs are smoothly compactly supported, here you can check that this requires the property that del f del zj bar is 0 on omega minus k. So f are holomorphic on omega minus k, right? So it will be killed by all this vector fields basically, but that is actually requires to say, I mean, actually you require that property to say that this is a CC infinity function in omega. Sorry, in Cn. In Cn. What does that mean? That means that there exists a U by solution of the Debye problem. So there exists a U which is CC infinity in Cn. This compactly supported is very, very important now. There is a CC infinity function in Cn such that del U del Zj bar is actually going to be Gj. What is basically happening, if you really look at Gjs, so this is happening on Cn, but on omega, what is Gj? So Gj is del f del Zj bar. So this is on omega. That means U minus f del Zj bar is actually 0. So this is for all j. For all j. That means that U minus capital F is holomorphic in omega. This is going to be your candidate. So U minus F, or rather F minus U, whatever the way you say, probably F minus U is the better way. F minus U. So F minus U is holomorphic in omega. So F minus U is holomorphic in omega, and what I have to show, so to show that F minus U is equal to small f on omega minus k. How do you show that? Okay, because U is a compactly supported function and the support is all what I said. The support will be always in the union of GJs, right? The support of GJs are always inside omega. So the support of this guy, the support of U will be always compactly contained inside omega. So if this is my omega, the support of this will something like this. So there will be at least some open set over here. So there exists an open set of omega minus k and connected open set. That's why connected is important. Open set such that U is 0 there, 0 on that open set. So F is equal, F minus U is actually equal to F on because capital F is defined near the boundary. Capital F is basically F. So on some closed some neighborhood of omega minus k, of neighborhood of boundary of omega by identity. Now you apply the identity principle. So identity principle, F minus U is F on omega minus k. So we have extended small f to holomorphically to omega. So that's the proof. The importance why I showed this thing is that because of this thing. This will appear, I mean, in SCV, how many times? I mean, I have seen like multiple times that this is actually appearing because this side is a smooth data. You solve the D-bar problem, you get a holomorphic function just by taking subtraction. Now, in the original D-bar problem, I mean, not the original means like with the more general D-bar problem, you will have D-bar problem with estimates. And that plays a very important role to construct holomorphic functions, not only holomorphic functions, but holomorphic functions with some nice estimates. So that is extremely, that's the reason why D-bar problem is so fundamental or so important in several complex failures. So that's more or less all. I just take 2 minutes because I just want to sum up what we did. So, oops, sorry. So this is the 4 lectures in a nutshell. So I hope it is visible. So what we did in lecture 1, we started with the definition of holomorphic functions. And we propose 3 definitions: existence of a C linear map, other one is the C analyticity, local power series expansion, and holomorphicity in separate variable or holomorphic in separate analyticity. What we at the end, what we talked, just talked, we didn't give any proof or anything, but this is an exercise that there are no isolated zeros. It's an exercise in the last lecture that there are no isolated zeros. I think you can now directly use the Hartogs phenomena to do this. And there are no Riemann mapping theorem. Solid disk and the ball are not biholomorphic, which even I didn't show. No compact singularities, which we basically talked about. So they're like the differences. There are lots of similarities, like the open mapping theorem, the strong strong identity principle. All of those things are there as a similarity. In lecture 2 and 3, we basically more or less talked about the 2 is completely about power series. We talked about, and 3 is a little bit about power series and a bit of a geometry. So 2, we talked about power series, and when the power series has a global power series and a Lorentz series expansion. So Reinhardt domain always have a Lorentz series expansion. Complete Reinhardt domain always have a global power series expansion. That raises the question of domain of convergence of the power series. And we saw in lecture 3 that complete Reinhardt domain with logarithmic convexity implies that that's the domain of convergence of a power series. That actually helps us to, we saw using this power series idea that all holomorphic functions, there are some domains where all holomorphic functions can be extended across the boundary. And that is what brings us to the definition of domain of holomorphy and the weak domain of holomorphy. Though the domain of holomorphy and the weak domain of holomorphy are basically the same. I gave a spoiler to the future lecture series, but this is not done yet. Sorry, this is not done yet, but domain of holomorphy and weak domain of holomorphy are the same. So they are the same notion. Today, what we did is just to the last thing is that the Hartogs extension principle, which basically also allow us to introduce the Dilbar problem and generalized Cauchy integral formula. So that's all I wanted to talk now about just one thing about generalized Cauchy integral formula is that, okay, so we solve the Dilbar problem in higher variable using the one variable result, but can we solve it using a concrete Cauchy integral formula in higher dimension, or rather, whether the generalized Cauchy integral formula holds true in higher dimension or not? That's a very interesting question, and the answer is no for all domain. I mean, it's partially yes, but okay, that's a very nice theory, and there is another that's another theory which is known as integral representation theory, and using that one can actually cook up the solution of Dilbar problem and explicit solution of Dilbar problem, which is very interesting. Maybe sometime some other lecture series we can talk about that. Here are the references which I actually wanted to give like over the last 3 lectures, but every time I forgot. So that's like the last thing about the references. Like this first book is my favorite one, is Ranga's book of integral representation in several complex variables. This is a very analytic book, that's why I probably like it. The next one is the Fitzgerald book. There's a little bit of geometric and a lot of algebraic stuff, but this is also a very good book. The third book is kind of a Bible. I mean, Kran's intro to SCV. It's a very thick book, and we probably find everything in it. It's very nice. And the fourth one, okay, I don't want to make any controversial statement over here, but this is the hard book to study if you are if you are a first learner. Hormander's book of several complex variables is a bit hard book, but it has a lot of stuff. So yeah, with that note, thank you very much.
So is there any questions? Okay, it seems like there is no question. So thank you, Agniva, for giving an
I think
excellent.
Nirmal, you have a question?
Like I am thinking
Okay.
this Delbar problem like a Dirichlet problem. So I just want to know about the uniqueness of the solution, because in the Dirichlet problem, the solution is unique on the bounded domains only. So here, like,
Right, but right. So what happens over the uniqueness is that I mean, see, if you solve the Dilbar problem just in one variable for the time being, suppose you have one variable and the second variable, another solution, then if you just subtract it, so you'll be, the way it works is that it's a one, so u1 minus u2 is a holomorphic functions, right? So it's a holomorphic function, it's a unique up to a holomorphic function. So that's how you can think. It's a unique solution modulo a holomorphic function.
But Dirichlet problem is unique if you give the boundary condition, otherwise it is not unique. So
Yes.
here, if you give, say, some boundary condition, then what can we say?
Exactly. So if you give some boundary condition, here we didn't put any boundary condition. I didn't write anything un1 equal to 0 on boundary or even equal to g in boundary. That I didn't write.
Yeah.
If I do that, then it will become it will become depending on the regularity, of course, but it will become a unique solution because U1 minus U2 will be 0 on the boundary. Now you apply a maximum modulus principle to say that U1 equal to U2.
Yeah, but this type of problem is solved. I think we saw in Italy the Lanzani solved this type of display problem, right?
Yeah.
The big boundary
Yeah,
condition.
this theory is pretty rigid. So I mean, there are very few
Yeah.
things left.
So it's a recent thing, I think.
Right.
Yeah. Okay. Any other questions? Okay. So finally, thank you, Agniva, for giving an excellent lecture series.
Yep.
And hope to see you in future to give the more lectures.
Yeah. Thank you.
Yeah, thank you, Agniva.
Yes. Thanks.